Yes, Samaj, start.
Yes. So good morning, everyone, all participants, and Dr. Varun, and coordinator
Good
of
morning, sir.
this FDB program,
Good morning.
Dr. Tiwari. Good morning. So welcome you again in the day 4 of FDP on Advanced Computational Fluid Dynamics. In this session will be delivered by Dr. Varun Goel on incompressible Navier-Stokes equation, solution of invested incompressible fluid flow. This is the second lecture of Dr. Varun Goel. He has also delivered his talk on governing equations on day 1 in session 3. So he has discussed very basics, different equations like continuity equation, momentum equation, Navier-Stokes equation, conservation of the species, etc. He explained very well all the basics of these fluid dynamics. So this lecture is in continuation with the first one. So I request now to Professor Varun, please continue your this session.
Okay.
So, please, sir, continue.
Thank you, Dr. Sharma.
Okay, thank you, sir.
So, I think this is the fourth day of this workshop.
Yeah.
Yes, yes.
So, I think you have gone through a lot many things about the CFD applications. So, in my previous class, I had discussed about the governing equations. Then we discussed little bit about the discretization of those equations. So basically now that is in continuation with that, we are trying to get some solutions out of those differential equations basically. That is what our objective is. So the problem is whenever we go through these equations or generalized governing equations, it is how to first of all represent your physical problem into the set of a mathematical equations. And again, your computer doesn't understand those differential or integral equations. Again, you have to convert those equations into some algebraic form of equations. Now, when those equations were converted into that algebraic equations, or you can say your simple linear equation set of, now again, because these are, you can say these equations can be a lot many types of equations. If I say initially when we talk on that day, that we talk about the conservation form of the equations, we talk about the non-conservation form of the equations. So there are steady solutions, unsteady solutions, incompressible solutions, compressible solutions. So there are many more combinations by which we get these generalized phenomena or generalized physical system into a set of your mathematical representation. And again, these set of mathematical equations, they again involve, these are the coupling equations. If I say, okay, we are not interested in the temperature, we are not interested in energy, okay, we go by the simple continuity and momentum equations. Sometimes we solve like this, and when we finally get the solution, we try to use those values of the converged solution into the estimation of the energy equations. But again, further these techniques have their corresponding limitations, because now when we thought in such that, okay, when we have a physical system, we represent that physical system into a very good mathematical system. Now I think all the problem is resolved, but it is not like this. There are many problems which are associated when we try to solve these particular equations, when we are able to get these solutions. Some are very exhaustive. It requires more computational time. Some are very difficult to formulate. In some situations, we are very having problems in solving the solutions. If you have heard one term, that is a staggered git problem, if you have heard of this particular word. If you are, चलिए जब आएगा तब बात करते हैं, तो स्टार्ट करते हैं थोड़ा सा लेट अबाउट द CFD techniques, and today I will try to discuss 2-3 techniques so that we are able to get how do we can program these set of equations to get certain solutions out of it. Again, their accuracy. So PPT is visible?
Yes, yes. Now it is visible.
Okay. So we are having a CFD technique, sir. Simple.
So screen is not visible.
कोई problem है?
No, it is visible. I think there will be some network error with that
Okay.
participant. Here it is visible.
So slide is visible to all of you?
Yes, yes.
Okay.
Yes, sir. Now it is
Okay.
visible.
So I start with a technique which is a Lex Vendroff technique. Now, if we go by this method, basically, this is a technique which is very good, give good results in whenever we talk of the solutions which are a hyperbolic or parabolic in nature. I think you all able to understand these set of equations, which equations are showing you a characteristic of a hyperbolic or elliptical or a parabolic. Normally that Laplace equation, you can see your temperature del square T by del x square plus del square T by del y square equal to 0. They are called as the elliptical equations. So they again characterize depending upon their b square minus 4ac value, and based upon that we can characterize them because they ease in getting the solutions out of those equations with the help of a certain methodology. So if we talk in terms of a marching solution, so this particular method will help us in getting those marching solutions very conveniently. But again, the algebra involved in this particular method is quite tedious. तो हम देखेंगे कैसे इसमें बढ़ते हैं. So that is a simple set of equations, continuity del rho by del t, that is equal to minus rho del u by del x plus u, del rho by del x plus rho del v by del y plus v del rho by del y. It is simple continuity equation. If you convert that all the terms in the left hand side, that is equal to 0. I think now we can say the x momentum equation. There is no body forces acting on this. We can say del u by del v that t equal to minus u del u by del x plus v del u by del y plus 1 upon rho del p by del x. Similarly, momentum in the y direction, we have considered this problem for the two-dimensional case. Del v by del t equal to minus u del v by del x plus v del v by del y plus 1 upon rho del p by del y. Now we have an energy equation, that is internal energy del E by del T equal to minus U del E by del X plus V del E by del Y plus P by rho del U by del X plus P by rho del V by del Y. So if we simply see, these are the 4 set of equations, and if you talk in these terms of an incompressible one, you can say, so we have to calculate the variables out of it. Now the question is, how do we march these solutions? So if I know the value at a previous time step, if I know the value of rho ijt, if my t is equal to 0, if I know the initial value of these, then I can say with the help of the Taylor series, I can get the value for rho ij t plus delta t, that is equal to rho ijt plus del rho by del t at ijt delta t plus del square rho by del t square ijt delta t square upon 2 plus and so on and so forth. Now the thing is, If I know all these values at the right hand side, I can get the value of the left hand side. And similarly, when I march in this particular row ij t plus delta t, then when I know all the values at rho I t plus delta t, then I can say, okay, rho ij t plus 2 times delta t. So similarly, I can marching the solution and I can able to obtain the solution with the help of this particular equation. Now the question is whether I can go by this rho ij t plus delta t equal to rho ij t plus del rho by del t ij t into delta t, and I now again I remove this particular term, that is rho. So my solution will become only, you can say, the error of the order of delta t only. But here we are considering of this that the error is of the order of second order in the time domain. So for that second order, I am using these three terms. If I further want to go on increasing the terms, I can go, but I will show you that it will lead to too much complexity, which is not able to manage. So we will keep it rho ij t plus delta t equal to rho ij t plus del rho by del t ij t plus del square rho by del t square ij t delta t square upon 2. So it means when I have to calculate this rho ij t plus delta t, I have to know this value. I must know this value del rho by del t at ij t. I must know this value del square rho by del t square. Now, okay, we will know this value, but how do we know this particular value del rho by del t? We can calculate this value with the help of the continuity equation del rho by del t equal to discretize these terms u del rho by del x plus rho del v by del y plus v del rho by del y. So when we discretize all these terms with the help of this, we are able to get the solution of del rho by del t. But the question is, how do we get this del square rho by del t square? For this particular value, we have to again differentiate this del by del t of del rho by del t, which becomes del square rho by del t square. It means we have to further differentiate these terms. Del rho by del t into del u by del x and rho into del square u by del x del t, which further, and this is our simple grid element. So similarly, if you see, we are able to get the solution for the uij t plus delta t, uij t del u by del t ij t delta t, similarly for the v, and similarly for the e. So with the help of this, we are having four equations, we are having four variables, and we are able to solve these four equations, four variable equation by using such equation. So we can say this is for rho, that is for the density, and similarly we go for this u, v, and e. These are a simple notation for the ij, I plus 1, ij plus 1, I minus 1j. That is a simple grid element which is showing what we will represent here. Now, when we are interested, now these four steps are clear to us, but the problem is for all these nodal points, we have to estimate this del u by del t, and similarly we have to obtain that del square u by del t square for all these values. Similarly, we know this value for the, you can say, your v, del v by del t, and similarly del square v by del t square, similarly for the energy condition. So if we see first of all that density, you can say del rho by del t at ijt. Now this is del rho by del t at ijt. Now we have to differentiate it because we are interested in estimating the values at del rho by del t at ijt. And how do I calculate this value? By using these terms. With the help of these terms, I am able to get the solution of this del rho by del t, which is minus, because the minus sign is there, rho ijt ui plus 1 jt minus ui minus 1 jt upon 2 delta x plus ui jt rho I plus 1 jt minus rho I minus 1 jt divided by 2 delta x. Similarly, rho ijt vij plus 1t minus vij minus 1t upon 2 delta y plus vijt rho ij plus 1t minus rho I j minus 1t upon 2 delta y. Can anybody tell me the accuracy level of this particular equation? Do it is of first order or second order? Second order. So if we simply go by the forward or backward difference, then we can say it is of a first order, but we are here considering in a discretization that is of the second order. So with the help of this, we can discretize, and now we are able to get the solution of del rho by del t at ijt. Similarly, we can estimate it for ij plus 1, ij minus 1, I plus 1j, I, or for all the nodal points which we are considering. Similarly, to estimate the value of del square rho by del t square, if we want to estimate the value of this del square rho by del t square, now what should we do? We differentiate del rho by del t, you can say del by del t of del rho by del t. And for this, you can say your equation will change now. And your equation is now minus rho del square u del x del t. It's minus is outside for every equation. So don't confuse, that is only a negative term. It's for all. So minus rho del square u by del x del t plus del u by del x del rho del t. So now the 4 terms will become into a 8 terms. Now you can say minus rho del square rho by del x del t plus del rho by del x del u by del t plus rho del square v by del y del t del v by del y del rho by del t plus v del square rho by del y del t plus del rho del y and del v del t. So these, now we have to evaluate all these 8 terms, and with the help of this, now we are in the position, okay, we can find it out the value of del square rho by del t square at ijt. And when we get this particular value, we can substitute in this, and we are able to get the solution at a rho ij t plus delta t. So the methodology is simple. We can get the values, but again the algebra involved here is little bit complicated. Now if you see del square rho by del t square, there is a mixed derivative, del square u by del x del t. Then you need your del u del x del rho del t. Okay, these are, we know del u by del x kya hai. We know del rho by del t, yes. We know del square rho. Again, we have to differentiate it with respect to x. So we can say del by del x of del rho del t. Then okay, del rho by del x, del u by del t plus rho del square v by del y del t, del v by del y. So if we have to calculate this del square u by del x del t, you can say del square u by del x del t. So you have to differentiate it with respect to del by del x of del u del t. So with the help of this, we are able to get the solution of del square u by del x del t. So del square u by del x del t is your, you can say, a simple term, that is, now you have this u del square u by del x square plus del u by del x square whole square plus u. So you, when you differentiate that term, it becomes now 2 to 4 to 6. Now 3 equations will come into a form of a 6 equations. Now with the help of these equations, you are able to get the solution. So del square u by del s del t at ijt is now equal to minus uijt ui plus 1j minus 2 uij plus ui minus 1j upon t upon delta x square plus again del u by del x again in a second order, so you can say a central difference scheme, ui plus 1j minus ui minus 1jt upon 2 delta x. Then we have the v, you can say your multiply by that del x del y. So we know the variation of that del u square u by del x del y in terms of, you can say, your, that is your mixed discretization scheme, which is again depending upon the extreme corners. So ui plus 1 and uj plus 1 plus ui minus 1 uj minus 1, they are in the plus, minus ui minus 1 j plus 1 t minus ui plus 1 j minus 1 t divided by 4 delta x delta y. Again we have the del u by del y del v by del t. So you can say a du I j plus 1 again in a, you can say, second order, and then you have 1 upon rho ij square p del p by del x pi plus 1j minus pi minus 1j upon 2 delta x, and then you have rho del rho by del x, that is so with the help of this discretization, we are able to get this single value of del square u by del x del t. Now for the estimation of your del square rho by del t square, you need to calculate this minus rho del square u by del, this is this one. Then you have del u by del x, okay, you can substitute, but again for this del rho by del t, you have to go by this equation. Then you again you have to find out this del square rho by del x del t by differentiating that equation with respect to x. Then del u by del t is known to us because we don't want any term in the time should be here. All the terms should be here in the terms of partial variables. So again del v by del y del t. So again we have to calculate this with this differentiating the term. Okay, then we have del v by del y, we know it, del rho by del t, again we substitute from the previous equation, and we can say v del square rho by del y del t, again differentiating, and then we can say del rho by del y del v by del t. So by all these substitutions, you are able to calculate this value of del square rho by del t square. So in comparison to this, if you see this equation del rho by del t, that is quite simple as in case of your del square rho by del t square. So if we consider a term that is a del rho by del t, that is much easier for us to get solution. If we consider only this term and we neglect this particular term, then we can say, okay, this is quite advantageous. Otherwise, So getting the solution of this particular equation is a very tedious task. So now we calculate all the values at this particular. Now we have this x and y. If we know this particular value at all the t level, when we march towards another time level, that is a t plus delta t, we can easily march the solution. And if we are interested in getting the solutions for the time interval, if you can say, okay, if we go by this for the t plus 2 times delta t, we can further go on in that particular time domain. Once, if we are able to get all these values of this, then we make a code according to the indices which are given here, and based upon that indices we are able to get the basic formulation for this. So that is what Lex Vendroff is. Now, to make a little bit simplification in the Lex Vendroff, because when we don't have any method, okay, then we will go by this particular method. But with the advent of this, the McCormick technique, around in 1970s, this technique was there. And around for 10-15 years, these techniques were very easily used until we developed the more rigorous methods by which we are able to get the solution. Because there are many methods, and depending upon the equations, those methods will prevail over one another. So now if we convert that equation that we have seen, rho ij t plus delta t equal to rho ij t plus del rho by del t into delta t. Let me forget this term on an average. And this will lead us to a quite simplified approach by which we can say that we are able to get the solutions. So if I just skip this word AV here and I say simply rho ij t plus delta t, that is equal to rho ij t plus del rho by del t into delta t. So the accuracy is of the order of first order. So it means now we are compromising with the accuracy. And if it say that error induced in the result is enormous, whether we get any convergence of the result, that might be a problem. So what to do so that it will help us in that particular term, which you can say your rho ij, sorry, to make it a second ordered term, and we are able to get the solutions. So let we write this in the terms of average, that we are taking of a certain average of this first order term, so that it would be helpful for us. Similarly, uij t plus delta t, uij t plus del u by del t average delta t, vij t plus delta t, vij t plus del v by del t average delta t, eij t plus delta t equal to eij t plus del e by del t average delta t. So in this, what we do, we estimate or we divide this problem in two steps. You can say a predictor step or corrector step. It means initially we predict something at a time level t, then we correct at certain time level, and then you can say, okay, this will help you us getting the solution with the help of this simple equation. Now we see the algebra involved in this particular method. So for the predictor step, del rho by del t at ijt, that is from the equation, you can see a simple equation which is this del rho by del t, rho del u by del x. So we have this. So you can say here rho ijt ui plus 1tj minus uijt delta x plus uijt rho I plus 1. So here what we are doing in a predictor step, we are considering a forward difference approach. So it seems that we are basically making a lot of compromises with the accuracy. Now we are again making it to be a first order. We are considering to be the first order time, and it is a first order in this space also. But we see how do we take care of that accuracy by introducing the second corrector step. So first of all, del rho by del t at ijt, that is calculated with the help of a predictor step. In that predictor step, we will go with the forward difference scheme. Now we have a rho ijt ui plus 1 jt minus uijt upon delta x plus uijt rho I plus 1 jt minus rho ijt upon delta x plus rho ijt vij plus 1 minus rho it is vij t upon delta y plus vij rho ij plus 1 t minus rho ij t upon delta y. So these all are in the forward difference, and with the help of this forward difference I am able to calculate my del rho by del t at ij t. So now I predict the rho ij at t plus delta t, that is rho ij t plus del rho by del t at ij t into delta t. And similarly, I can calculate this for the u, v and e. So now we have calculated a first step, that is rho bar ijt plus delta t. Now in a corrector step, that is a del rho by del t at ij t plus delta t, again I am using the same equation, that is this one, del rho by del t, the continued equation, but it is at a time step t plus delta t, which is again your predictor step rho ij t plus delta t, this one, rho ij t plus delta t, this one. Then we have this u bar ij t plus delta t, this one, u bar I minus 1 j t plus delta. So we basically know all these values by the predictor step. But again you observe here that we are using a backward scheme here. Initially we are talking of the forward scheme, but here we are talking of the, you can say, your backward scheme. So now you can say we are taking care of this forward and backward. So now the solution which is available to us, that will take care of your, you can say, in the time as well as in the space dimension, that is equal to the, you can say, your second order. So we are not compromising with the accuracy, but we are getting the results which are in consistency with the results which are available to us, and with the help of this we are able to get the solution without going towards the del square rho by del t square at ij t. So here if you see this rho, that is a predictor step density, then u bar ij t plus delta t minus u bar I minus 1 j t plus delta t delta x plus u bar ij t plus delta t rho bar ij t plus delta t minus rho bar I minus 1 j t plus delta t upon delta x plus rho bar ij t plus delta t v bar ij t plus delta t minus v bar ij minus 1 t plus delta t upon delta y plus v bar ij t plus delta t rho bar ij t plus delta t minus rho bar ij minus 1 t plus delta t divided by delta y. So now with this, we are able to get all the values which are available at del rho by del t ij t plus delta t. Now with the help of these equations, we are able to get the again a del rho by del t value at ij t plus delta t. So for this, now what we do, we calculate the del rho by del t average. So now we are considering at a time step ahead and time step back. You can say t and t plus delta t. Now this will help us in calculating the, you can say, your average value del rho by del t average, which is the average of half del rho by del t at ijt, which is a previous time step. That is, you can say your that is your this one del rho by del t ijt, and this what we have calculated here del rho by del t ij t plus delta t. So with the help of this, we are able to get the solutions. Now we get the del rho by del t average, which is taking care of your time, and which is the order of. Now you can say rho ij t plus delta t equal to rho ij t plus del rho by del t average into delta t. So you can say your del rho by del t average is a representative mean value of del rho by del t between times which is occurring at a time level t and t plus delta t. So if you compare this with the counterpart, that is, you can say a Lex Van Droff, the time derivative which are evaluated of the second order del square rho by del t square is necessary to obtain a second order accuracy, whereas here the rho by del t average is to preserve second order accuracy without the need of doing calculation depending upon that del square rho by del t square. Similarly, we are able to get the solutions for u, v, and e values, and accordingly we can march in the further time domain. You can say a t plus delta t, then further we can move first t plus 2 delta t. So similarly we can go in that particular direction. And you can say the procedure by which you can go for the predictor step, or you can say a corrector step by going forward and rearward, you can interchange even. That will not lead to any error in this. So you can do either you take a rearward in the predictor step, or either you can go for the, you can say for the forward difference in the corrector step. That can help your problem in the solving. You can get the solution with the help of that particular thing. So I just want to now show you a simple grid. Is if let's suppose we have such a checkerboard velocity distribution. Sometimes in our problem, if we get that, if I say it is a I plus 1 and this is your I minus 1, similarly if I say a j minus 1 to the j plus 1, and if these values And if I try to write it down like this, ui plus 1 minus ui minus 1 divided by 2 times delta x, then every time I will get the value that is a 0. So such kind of a problem is called as a checkerboard problem. And we face sometimes in where we are talking of the incompressible type of a problem. Now, this is basically a special kind of a problem, you can say. Now, if we are interested to solve our problem with the help of any another algorithm, and you can say a staggered grid, what does it mean basically? If we are interested to solve these equations with the help of simple or Mac algorithm, now what does this staggered grid is there? Why we use this staggered grid? Is there any method by which we can move towards that and we are able to get the solution of this, and we are not interested in it? So what do you mean by this staggered grid? So if we have, let's suppose I have shown you some values, that if the values occur the same at both the ends, and we are interested to see take the values there, then we will not get any effect out of it, because at every time we are getting the solution that is equal to 0. And doesn't induce anything in that. And for to solve such kind of a problem, we shift our normal formulation towards the staggered grid formulation. So if you see simply here that we are representing here three terms: a u velocity, a v velocity, and a pressure. If you observe that what we are observing, all two are at a surface, but we are observing pressure at the intermediate point, so that we can solve such kind of a problem if we have a checkerboard type of a problem also. If my solution is coming like this, or if my initial solution is like this, still I choose an option of a staggered grid. It means the two values are defined at a edge as a node, we can say, but the another third one, that is a pressure, that can be defined in the middle. And you can see that if you take for the V values, then this is your control volume. And if you take in terms of a V, U, but again for the X, it becomes your main control. So it basically type of with some staggered indices, you can say. They are not following a complete pattern. Pattern to hoga, but it is not a very, they are not occurring over the entire edge, every value. So one value is coming at this, and that is a pressure. So we use this staggered grid out of it. So if we are interested in solving the Navier-Stokes equation here, so if we talk about the semi-implicit method for pressure linked equation algorithm, if you talk in this term, you can say iterative pressure first, that pressure is estimated. You guess that pressure, and then you can say that pressure is your star. So we use this star for the estimated pressure. Then we use this pressure, star pressure, for the solved U, V, and W. And these values are as corresponding velocities. Then what we do, with the help of that guessed value, we try to satisfy this UV, U star, V star, W star, and then we try to validate the continuity equation by using these U star, V star, and W star. When our continuity equations are not satisfied, then there is a certain term which you can say, or we add certain pressure, which is called as a pressure correction. And with the help of that pressure correction, we are able to get now a pressure is P star plus P corrected. And with the help of that, again we estimate the value of U, V, and W, which is U star and U prime. That is a initial guessed value to the corrected value for the VW. And then finally we can get, when this satisfy the continuity equation, we said, okay, now our equation is satisfied and we are able to get these solutions using these equations. So that is a simple term of a, you can say, your simple algorithm. These are the steps which we have mentioned here, which are discussed. Start guess, estimate the value from momentum equation, introduce the correction, and express these values, substitute the value into continuity equation. Then we can solve the value of other equations if we have a. And if our solution is converged, okay. Otherwise, if it not converge, then again go on the correcting the values. So that's all from my side. Now, any doubt from your side?
Hello. You can ask any doubt you have.
So I
Please
try
write in
to
the chat box.
I try
Yes,
to
sir. Yes,
discuss
sir.
these 2-3 methods.
Hello, everyone. Have you any doubt?
Any query from participant side? Any query from participant side? No query.
So, can we stop here?
Yeah.
Okay, sir. Thank you so much, sir, for your talk. In this lecture, you described very well how the Navier-Stokes equation is solved, staggered grid pattern by converting it into algebraic equation or in discretized form. So it will definitely benefit it to all of us. It was very enlightening lecture. Thank you so much. Now I would like to invite Professor Sinha sir from IIT Lucknow. Please connect and give vote of thanks to sir. Hello. Hello.
Thank you, Dr. Ajay.
Okay,
And,
sir. Okay.
and good afternoon to all of the participants. It's my pleasure to propose vote of thanks on behalf of the Institute of Engineering and Technology, Department of Mechanical Engineering, and myself. I express sincere thanks to Professor Varun. He is a professor at NIT Hamirpur. He delivered the lectures in so beautiful manner that he made this complex topic of CFD is a very simple, looking very simple to all of us. And I am sure that the knowledge we are gaining from this lecture or we gain from the lecture of Dr. Varun, it will be helpful for many of us because many of the participants, they are doing the research work also. So as far as this knowledge will help us in our studies, in our future research, and also it will be very, very helpful to our students to whom which we will deliver this knowledge. And once again, I would like to thank Professor Varun for taking out time from his busy schedule and to be with us in this faculty development program. And so for this, I am very, very thankful to Dr. Varun. Thank you so much.
Thank you, sir.
So next session will be at the 12:30 by Dr. Sen. Thank you.
Okay.
The
Thank you.
attendance, okay, sir. Thank you, Dr. Man. Thank you. Attendance link is shared in the WhatsApp and Google Meet also. Can you fill it? Kindly. Okay. Deep sir, good morning.